So today we're talking about integration estimation. There is going to be a point right now in our class where we don't have a method to integrate. That will change in Chapter 8. Okay, so for example, at this moment we cannot solve the integral of e to the minus x squared dx. It's a nice looking curve. It's like a bell curve. So certainly we could go from 1 to 0 and get that area under there. And so what we're trying to do is have a way to get really close, right, to that, what that area is. If we talk about this integral to infinity, right, and it was divergent, then we wouldn't even care about the estimation, right? There's that subtle difference of what I'm talking about. Is this a good model for us, or is it going to fail no matter what, right? So if we think it's a good model and we can estimate, we'll do that, okay, until we come up with new methods. And then the newest method we'll do with integration is something called Maclaurin series and Taylor series, which is in Chapter 8. We turn our function into a series, a sum of polynomials, and then of course integrating or differentiating polynomials is very easy. So, but the idea here is we can't solve this, but we can get pretty close to the area, right? In fact, so we have a bunch of integration estimation methods. And then we have error estimations for each of them. The formulas are complicated, but you're going to have them on your formula sheet. Don't need you to memorize them. Even when I was face-to-face, I wouldn't make students memorize these because, I mean, one, you're never going to do one of these by hand outside of this class, right? You're going to use a computer method. You're going to use some computer system that's designed by our computer science students in the class to get the estimation of the area of the solution. And remember, and you'll see this in Chapter 6, solutions to integrals are forces. So in physics, a force, how much work it takes to push a car up a hill. Estimations, answers to integrals in biology or the amount of medicine in a bloodstream left over in a blood system. For computer scientists, area under curve is probability, right? So probability is something we deal with all the time in computer science, right? So all of these integrations results will be a part of our results in our field of study, right? So all I care about is that you can do the integrals. That's what I care about as a mathematician. I don't so much care about the applications, and I especially don't want to teach computer scientists the bio applications. And God forbid I would teach the engineering applications to the biologists, right? So that's why I do the project. I do the project so that we can each kind of work on the applications of integration to each of our fields. So anyway, these integration methods, these estimation methods, are rectangles. Left or right endpoints. In Calc 1, I only taught the right endpoint rectangles. You might have had a teacher that taught both. Midpoint rectangles, so midpoint rule. Right, so the first one, the rectangles. I've got some curve, right, and I'm estimating the area under the curve using, and so you can see the height of the rectangle is from the right endpoint, and the bases are all equal, right? So delta x is the base, and the height is f of x. So I get that rectangle, and I add them up, and I get the estimate. Midpoint is really close to that. It's just that instead of it's a right endpoint rectangle or a left endpoint rectangle, I get the height of the rectangle from the midpoint, right? So when I draw my rectangle, I use the midpoint as the height. So this is delta x, and the midpoint is giving me my height, f of x sub 1 plus f of x sub 2 over 2, right? So add the two endpoints and divide by 2 to get the midpoint. So those will be pretty similar. And then the trapezoid rule. So for the trapezoid rule, I am kind of doing the same thing. I'm drawing the rectangle, but I'm connecting the diagonal from left endpoint of the curve to right endpoint of the curve. So this one's even better, right? Is that making sense? The pictures I'm drawing, right? So we're doing different geometric shapes underneath to get areas, and then summing up the areas, right? And then the one that really works the best is Simpson's rule. Simpson's rule is I take an even number of partitions, let's say 4, and I connect 3 points, and I draw the parabola. So I draw the parabola there. I get an ax squared plus bx plus c. And then I take the next 3 points, and I draw that parabola. And then the next 3 points, and draw that parabola. And of course, the parabola is very easy to integrate, right? It's a polynomial, so very easy to integrate. And depending on the shape of the curve, one of these will be perfect, one will be very good, one will be weak. But we tend to, Simpson's rule gets better and better as, all of them get better and better as we make more rectangles, right? So I'm not really doing rectangles in the trapezoid unless I think about doubling the trapezoid. If I double the trapezoid, there's a nice rectangle to think about. And the parabolas, right, I've got some curve on top, but I still think of them I still say rectangles, even though they're not. They're partitions where the top is a parabola, and then of course it's easy to get the area underneath the parabola, right? Each of these has an error method as well. We're only going to test on Simpson's rule, okay? So in the WebAssign, you could have a trapezoid and a midpoint, but on the test I will only ask about Simpson's rule. So you only need to know the Simpson's rule formula and the Simpson's rule error, okay? And that will be our main focus of the error will be the focus of the last 45 minutes of the class, okay? And so this next piece will be just doing a couple of area estimations using the other methods, including Simpson's rule. So I guess it wouldn't be a bad idea for me to go back to Calc 1 and do a right-hand rectangle piece. Probably won't be a bad thing for me to do, right? So it might just be easier for me just to jump right into an area estimation for each of these methods, and then if you really desire to see where they come from, I could show them to you. The only one I won't do that for today is Simpson's rule. That would take about an hour to do alone, just to show where the formula comes from. But I will post a link today, especially for Charlie and Adrian, to take a look at about the derivation of Simpson's rule, where it came from. And the rest of you, if you're a glutton for punishment and you have nothing else to do, feel free to look at it. I would not do it, but I want my math majors to do it, because when you do all of this advanced calc stuff, you're going to be proving all of this, right? When you do your 300 level advanced calc and 400 level advanced calc, you'll prove everything we're doing. Oh, so let's see if we can just go back to Calc 1 and do a quick right-hand rectangle, okay? And I'm going to use a sine function for each of these for now. I'm looking at sine of x from 0 to pi. And I know it's symmetrical, right? So I could really do even just half of the integral. But let me do the whole thing, right? And of course we know the actual answer here. And this is something I like to do on my exams, especially the final exam, is I will give you a problem to actually tell you to find me the area. It will have to be like done by parts or something, you know what I mean? Not this simple. And then estimate using Simpson's rule and see how close you get, and then see if how good the error is, right? So it's kind of what we'll definitely do that today. So, but let's do this. Go ahead. Question.
All right. Will we be doing the Simpsons rule tomorrow?
Today. Everything today. I don't want to do this again. I want to get all of this done today and be done with it. And again, you'll see the homework in 5.9, which I forget which number it is. It's the next number. It'll have one problem with midpoint rule, trapezoid rule, Simpson's rule. And in the attempts to show you Simpson's rule gets better. And then I think there's another problem with Simpson's rule that we have to do on Excel. Oh, no, that's not true. You know, and if I even, and you'll see it wasn't on my last semester's test because I didn't have calculators. I had students without a calculator, so I couldn't do it. I would never make you do this by hand. I would want you to do the final answer on a calculator. I'm going to do most of these by hand, but what is this one? What's the antiderivative of sine? Antiderivative of sine is what? Minus cosine? So I get minus cos of pi plus cos of 0, right? So that's minus a minus 1 plus 1, so I get an area of 2. How are we doing there? Yes? Okay. Good. So we know the actual area. So then we're going to do some estimation methods and then see what happens. See how close we get to 2 with each method, right? And this is a pretty cheap one. But it's just I want you to see the process. I don't need it to be a perfect result. So I'm going to start with right-hand rectangles, and I'm always going to use 4 partitions. If I give you a question like this in the test, I give 4 partitions. You'll see Simpson's rule will ask for 8. The book will ask for 20. Oh my God, what a pain. So we're going to do right-hand rectangles. This is from Calc 1. And 4 partitions. And we're going to do 4 partitions every time. Simpson's rule needs even number of partitions. So 2 would work, not that well. 4 would work. 6 would work. 8 would work. Of course, the more partitions I give you, the more rectangles I give you, the more work it is, right? So I'm trying to make it as little work as possible when we do this. So looking at the picture of the 4 partitions from 0 to pi, I want to cut pi into 4 pieces. And so obviously each width, and they're always going to be congruent, right? The widths are always going to be equal measure, okay? So I'm going to take my delta x here to be pi minus 0 over 4, so pi over 4. So each width of my rectangle is going to be pi over 4. And then I'm going to get my height from the right-hand edge of each base. So I'm going to go up to the function from right-hand edge, up to the function right-hand edge, up to the function right-hand edge, up to the function right-hand edge, and then draw those rectangles. Now you'd say from the first 2 you definitely have an overestimate, but from the next one I get an underestimate, and the last one is 0, right? That last rectangle has a height of 0. So I want to calculate each step x sub I, right? So x sub 0 is my first, x sub 1, x sub 2, x sub 3, and if I do 4 partitions, I'll always go up to x sub 4. Does that make sense? So x sub I is counting, right, the ticks on the x-axis. So x sub 0 is 0, x sub 1 is pi over 4, x sub 2 is 2 pi over 4, x sub 3 is 3 pi over 4. You did this in Calc 1. Does this remind you of something we did in Calc 1? Anyone? Adam, yes. Anyone else?
Yes.
Sarana, yes. David. And so if you had a really demanding teacher, they did everything. They did right-hand rectangles. They probably did midpoints too. I only did right-hand because I'm lazy and I get bored. So I can see here that my rectangles, I have 4, right? So R sub 1, R sub 2, R sub 3, R sub 4. The area of those, right, is always going to be delta x times the height, right? So delta x times the height, and the height is always coming from x sub I, x sub 1, x sub 2, x sub 3, x sub 4, right? The right-hand sides of those. So the rectangle 1 is pi over 4 times sine of pi over 4. And the next one is pi over 4 times sine of 2 pi over 4. And then pi over 4 times the sine of 3 pi over 4. Make sure you're with me here. I don't want you lost here because we're just starting today and it gets worse. So make sure you're with me. I'm getting the base of the rectangle from the width, delta pi over 4, which I got, and I'm getting the height from that right-hand rectangle. And you can see the height has an x-axis value of x sub 1, x sub 2, x sub 3, x sub 4. And then I'm plugging that x value into the function to get the height of the rectangle. So my area estimation is the sum from I equals 1 to 4. You remember all this sigma notation, all the fun we had with that, of delta x times f of x sub I, which we already figured out, is pi over 4 times sine of pi over 4. In fact, let me just factor out each pi over 4. So sine of pi over 2 pi over 4, sine of 3 pi over 4, sine of 4 pi over 4. Right? So I factored out that pi over 4, that delta, that base of each rectangle. I factored that out. How are we doing here? Don't let me lose anybody. Josh, how am I with speed? And I'm not asking. Good. And I'm not asking you because I think you might need more time. I'm asking you because you've been the one to say to me, "Yo, slow down," and I want you to say that. Okay. Tonight, you okay here?
Yeah.
Yeah.
Good. Hey, Bruce?
Yeah, I'm good.
Michael?
I'm okay.
Okay. So, when I do a problem like this, I want to carry it. Thank you, Angel. I want to carry it as far as I can before I go to my calculator. I want to go as far as I can with with the exact answer before I go to my calculator. But so I've got a pi over 4 up front. I know sine of pi over 4 is rad 2 over 2. Sine of pi over 2 is 1. Sine of 3 pi over 4 is rad 2 over 2. And sine of 4 pi over 4 is 0. So it looks like I get pi over 4 times 1 plus rad 2. And that's a nice answer to give me on a test. And then, of course, you can get me a decimal. And I get about 1.8961. Two decimals is fine. We're humans, we like 2 decimals. You scientists like synthetic, no, what is it? Sig figs. Ugh. 4 decimals is what the book will usually give. I used to write every decimal my calculator would give me, and then round to wherever the hell I wanted, so the teacher could see that I was definitely getting the right answer. So not too far off of 2, right? So this is a pretty good estimate already. I mean, if we were thinking about it, it's only off by a dime, right? Of course, a dime for every $2, a nickel for every dollar is pretty bad when it gets to $1 million, but it's not too bad. So our Calc 1 process was pretty good, right? Our Calc 1 process was pretty good. In fact, what did we do in Calc 1? We did a limit to see how many, and when we got an infinite number of rectangles, we got the exact area, right? But we're not doing that limit process this time. We're just, remember what we're saying is, we have an integration method that we can't do. We don't have a process for it. But we think the problem is still viable. So we want to get an estimate. We want to be able to have a way to get an estimate. All right, so that was right-hand rectangles, right? So let's go to the midpoint formula. And this thing's it's just a pain. It's just a pain, this stuff. I'm sorry, I can't hide my true feelings about it. Let's do the midpoint formula. So the midpoint formula should be very straightforward. I shouldn't really have to explain anything crazy about it, but I'm going to keep it as 4 partitions, right? I'm going to keep it as 4 partitions every time. Every one of these methods I'm doing 4 partitions. 4 rectangles, if you will, in some cases. You don't have to have the midpoint rule on your formula sheet. You don't have to have the trapezoid rule on your formula sheet, only Simpson's rule. So here's the midpoint rule, and you can see it's the same thing. The integral from a to b of some function f of x dx is delta x times the same thing I just had, but I'm taking the midpoint for the height. So I don't, right, because I'm not asking you to know this formula or use it, except for once in homework. I didn't really need to do that. It's better for me just to draw my picture, right? So I already know my 4 partitions. Oops. I used to draw them a little bit evener. And I know this is pi over 4, 2 pi over 4, 3 pi over 4, 4 pi over 4. And then clearly, though, I want to get the midpoint of each one of these. Right? I want to get the midpoint there. So I'm going up to the function at the midpoint, but my top of my function is going to cross to each of those. Right? Is that making sense at all? So I get the height of the function at the midpoint, but the rectangle still goes from x1 to x2, x2 to x3, etc. So I've got to figure out what x sub 1 bar is. Right? It's the midpoint of 0 pi over 4 plus pi over 4 all divided by 2. So pi over 8. So pi over 8. And then I do the same for x sub 2 bar. That's the midpoint, right, for rectangle. So that's what it's 5 pi over 8. I can just see it, right? I'm sorry, 3 pi over 8, right? Sorry. I'm adding the two numerators, right? Pi and 2 pi over 4 and then dividing by 2, so the over 4 becomes over 8. And now I see 1 pi over 8 and 3 pi over 8. I know the rest, right? What's x3 bar? It's 5 pi over 8. And x4 bar is 7 pi over 8. Is that okay with everyone? Delta x again is b minus a over n. So that was pi minus 0 over 4 or pi over 4. For all of my problems, my delta x is going to be pi over 4. I'm doing four partitions every time. Will it be like that in every problem? No. So you have to calculate how wide. If you cut your region into 4 equal regions, how wide is each base, right? That's my delta x. So my function is sine of x. So here we're going to get an area that's approximately equal to pi over 4 times sine of pi over 8 plus sine of 3 pi over 8 plus sine of 4 pi over 8. Now these all could be done with half angle formulas. I'm not going to do that to you. Right? We learned how to calculate half angle, right? Sine of a half a theta. We learned how to calculate that in Trig and in pre-cal. I'm not going to do that. Let's go right to the calculator for this one. So I'm doing, and I'm in radians, right? And so I'm just doing my sine of pi over 8, sine of 3 pi over 8, all of that first, right? Sorry, did I make a mistake? Yes, 5 and 7, right? Sorry. Anybody catch that? Sine of pi divided by 8 plus sine of 3 pi divided by 8 plus sine of 5 pi divided by 8 plus sine of 7 pi divided by 8. Oh my god, I'm bored. All times pi over 4. .05. 23. So an overestimate, which kind of makes sense if you look at the picture. It could be an overestimate. It's not far off. If you remember, our right-hand rectangles were under by a nickel, by 0.05. These midpoints are over by 0.05. And of course, we know as we do the limit, right? Those two areas are going to shrink toward each other, toward the actual area of 2. How we doing here? So midpoint rule, so when you're doing these, like when you go do the one on WebAssign, you just got to be precise. You have to be organized. If you can see, I'm writing out my delta x, I'm writing out my x sub i's. I've got my formula. I'm trying to be organized. I'm trying to use the calculator as little as possible. This one I needed the calculator pretty quickly, right? All right, but we're ready for trapezoid, okay? So the trapezoid rule takes a little bit more work to understand. But we're going to have, we know the integral from a to b of f of x dx is going to be delta x over 2 times f of x sub 0 plus 2 times f of x sub 1 plus 2 times f of x sub 2. So I have all my middle coefficients are going to be 2. F of x sub 3. And when I start at f of x sub 0, it's a coefficient of 1. And when I end at f of x sub 4, it's a coefficient of 1. And remember, I'm only doing 4 partitions. So, of course, if you have more partitions, you need more terms, right? But you'll notice here that all of the coefficients in the middle are 2, and then the endpoints are a coefficient of 1.
So if you had 6 partitions, it would still just be the first and the last or one?
Exactly. And where that comes from, I'll show you, okay? It's easy to see it from the trapezoid rule. It's not so easy where the coefficients are going to come from the Simpsons rule. But I don't want to spend an hour. I don't want to waste an hour of your time. I'd rather just us say, okay, we trust this English or whatever he was, whatever the person was. Maybe it was, I don't even know. It's definitely, it wasn't a female, but there's some great female mathematicians. It's just, you know, not at the time when all of this stuff was going on, and not because of anyone's fault, but the men. But in this particular piece, right? If I look at, so in this particular piece, there's my sine, and if I look at my 4 rectangles again, so for example, if I just look at this rectangle here, I'm actually making it a trapezoid, right? Right, so it's a trapezoid. And if you remember, I don't know what grade it was, we learned how to get the area of a trapezoid by doubling the area. So 2 times the area of the trap was the first height 1, plus height 2, right? Notice that this is height 2 over here, and this is height 1 over here, right? So my new height is height 1 plus height 2, and my base is delta x, right? So I had a delta x times height 1 plus height 2. So, right? So that's that red trap. But what about this green trap? Right? And I'm not saying they're the same height, but so 2 times that area of the trap, and this is now height 3 over here, is delta x times height 2 plus height 3. So you can see how many height 2's am I getting there? Right? How many height 2's am I getting there? And remember, height 2 was an x sub 2. So I'm going to get 2 of those height 2's. And then what am I eventually going to have to do? Divide everything by 2, right? And so that's where this divided by 2 comes from. So the divided by 2 is canceling that doubled area of the trap. And then each of my inside heights get doubled. And that's why I get a double height for each of those inside heights, but not for the outside height. Right? Not for that x sub 0. That one never gets counted twice. And the x sub 4 never gets counted twice. So that's where those things are coming from. Okay? And if you want a slower version of that, you can just simply you can Google derivation of the trapezoid rule, Calc 2, right? But you're going to waste a lot of time. It's pretty simple little geometry there. Hopefully I'm convincing you. But so what am I going to do in this? I need to find my delta x. Well, I know that's pi over 4. It's the same as everything I've done, right? And I know my x sub 0s. I know my x sub i's. So there's a lot of repeat here, right? And that was 0 pi over 4 plus 1 pi over 4, 2 pi over 4. Yes, there is a coincidence, 3 pi over 4, 4 pi over 4. So you see that leading coefficient is coming from my subscript, x sub 0, 0 pi over 4, x sub 1, 1 pi over 4, x sub 2, 2 pi over 4. And so now I'm ready, this integral from 0 to pi, that's sine of x dx, is approximately equal to pi over 4 divided by 2, right? My formula says delta x over 2 times sine of 0 pi over 4 plus 2 times sine of pi over 4 plus 2 times sine of 2 pi over 4 plus 2 times sine of 3 pi over 4. How are we doing? Plus 1 times sine of 4 pi over 4. How are we doing? Everyone okay? I feel like I might be going too fast, but you're going to stop me. Thanks, Caleb. Anybody else all right? Anybody? Charlie, you okay? Adam, thank you. Haoshen, thank you. Eleanor, you there? Nice. David, yeah? Most of the people I'm calling out, I can see them, so I can see them nodding. And then, like, Sorana just gave me a thumbs up, and so thank you, Sorana. Right? Right, if we were in class, Charlene, thank you. If we were in class and you were asleep on the desk, I'm not going to call on you. In high school, I would throw an eraser at you, but I got fired. I'm just kidding. I would throw the eraser. It doesn't hurt too much. So we can simplify this quite a bit here, right? This is now pi over 8 on the outside, and sine of 0 is 0. Sine of pi is 0. So I've got 2 times square root of 2 over 2 plus 2 times 1 plus 2 times square root of 2 over 2. Hey, look at that. It's almost like before, right? I can factor out the 2. And again, you don't have to do stuff like the way I do it. And then I get the same answer as before, 1 plus rad 2. Yeah. Well, look at that. That's the same answer as I had before, right? Isn't it? Did I make a mistake? Factor out of 2. Get 1 plus 2 rad 2 over 2 is 1 plus rad 2. I think it's the same answer. Which is kind of interesting.
Yes, it is.
Yep, same answer. And that's fine. Right, 1.8961. But what you're seeing is with 4 partitions, these 2 methods, 3 methods are already, right? Right-hand rectangle, they're close, okay? What happens is you do more partitions, you get a better estimate, and you're going to get a better estimate out of the trapezoid than you are out of the other 2 methods. So kind of like saying, well, why bother with the other 2 methods now? And that's why I'm going, well, let's go to Simpson's rule, and it's going to be even better, so why bother with the others, right? And so that's why I restrict it just to Simpson's rule on the exam. But the geometry here should be kind of, does anyone agree with the geometry is kind of simple here and you kind of get it? Or, yeah, David's there, Eleanor's there. Charlie, you okay with the geometry?
It's not like Demon Sums.
Go ahead, Michael, say it again.
It's not just like Demon Sums.
Yeah, it is. They are Riemann sums, exactly. And the Riemann sums, they don't all have to be the same width, and then you're doing those limits, right? So, yeah, but it's if you did it in Calc 1, this is not much different in Calc 2. In fact, and because I'm giving you the formula sheet, it's really not that difficult. But we want to show that Simpson's method gets even beat by our Maclaurin series method in Chapter 8. That's our ultimate goal here. Is that so this integral can't be done, but we can get a nice estimate of it with Simpson's rule, and then we're going to get an even better estimate with it with the Taylor series, with the Taylor series, Maclaurin series, and that's Chapter 8. All right, Simpson's rule. We'll do this, and then we'll do it with the sign, and then we'll take a little break, and then we'll get in a little deeper with the Simpson's rule. We'll try another level problem, and then we'll look at the error for Simpson's rule, and we'll be done, right? And then hopefully I can not do too much tomorrow to give you a weekend to catch up and get some things done, right? But here we go, Simpson's rule. The coefficients aren't going to make sense. I mean, they might a little bit, in that some of these rectangles with the top being a parabola will be repeated several times, and some will only be repeated a few times. But really, the derivation, which is very long, takes quite a bit of time. So here is Simpson's rule. And because I'm doing 4 partitions, I'm writing it out for 4 partitions. Because I'm going to give you 4 partitions in the exam, you can write it out in 4 partitions for your formula sheet, right? But if they ask you a problem for 6 partitions in your homework, you just have to extend it, right? But if you have trouble with it, you just ask me. So the integral from a to b of f of x dx is approximately equal to delta x over 3. 1 times f of x sub 0. So again, I'm going to start and end with a 1, but then I'm going to alternate with 4 2 4s. So 4 2 4 2 4 2 4 2 4. So it's going to be a 4 2 4 pattern. So 2 times f of x sub 2 plus 4 times f of x sub 3 plus 1 times f of x sub 4 again. I think that Charlie and Adrian, the one I'm sending you is from MIT. the guy who derives that one I like the best is he's from MIT. So pretty smart person, or at least they got into MIT. So we know all of these numbers now, right? We know delta x. We know x sub 0 through x sub 4. So we can jump right to this formula, right? So what am I getting? I'm getting pi over 4 divided by 3. And I'm getting sine of 0 pi over 4 plus 4 times sine of pi over 4 plus 2 times sine of 2 pi over 4 plus 4 times the sine of 3 pi over 4 plus the sine of 4 pi over 4. And you see, I'm just trying to stay as organized as I can. When I do a problem, I figure out delta x. I do a problem, I figure out my x sub zeros. Maybe I draw a picture. You know, I get the formula down, I fill into the formula. I do as much as I can without the calculator, right? So I've got a pi over 12 here. I've got a 0. 4 times rad 2 over 2 plus 2 times 1 plus 4 times rad 2 over 2 plus 0. It's pretty easy. This is not that bad. It's just boring. I'm sorry, I'm not supposed to say that. Do other teachers say when they're bored? Do teachers tell you when they're bored? Adam, they do? Good. So I'm not. My parents used to say to me when I was a kid, why can't you be unique? Be unique, just like everyone else. That's funny. So I get 2 rad 2 plus 2 plus 2 rad 2. I'm going to factor out that 2, so I get a pi over 6. And I get 1 plus 2 rad 2. And then I'm going to my calculator. Ooh, it's better. Off by a half of a half a penny. It's off by a half a penny, right? 0.005, half a penny. Just with 4 partitions, right? I mean, think about it. When we were doing area with Riemann sums in Calc 1, we had to use an infinite number of rectangles, right? But we get pretty close pretty quick, right? But we want in Calc 1 we wanted the exact area. Here we know we don't have an integration method that works yet, not till chapter 8, right? So we've just exhausted, by the way, all of our integration methods. Thank God, right? We had about 15, 10 from Calc 1. If you get picky about my list, maybe it's less. And then we had 5 from Calc 2, including shortcuts and things like that, variations. And now we're saying we're out. We don't have any more. Nothing else works. We haven't discovered it yet. So, but we might be able to estimate, and that's what we're doing here. All right, let's take a break. All right, so it's 10:05. Let's come back at 10:15.